Hello, my name is Andrew Vogel of the Math Science Technology Center at Paul Laurence Dunbar. My project is predicting tweet engagement with deep neural networks. The 30-day prevalence of e-cigarette use among 12th graders is 6.2%. Conventional cigarettes is 11.4%. How can health agencies improve engagement on Twitter, where engagement is favorites plus retweets? Can we use interpretable models to predict tweet engagement and extract features that are indicative of an engaging tweet? The goal of my project was to use deep learning to predict tweet engagement. First, I created models that predict tweet engagement. I trained them on tweets by @FDA Tobacco, and I evaluated the models using tweets not trained on the training dataset. So I crawled 4,417 tweets from the @FDA Tobacco Twitter address. I culled the retweets. This data had a lot of zeros and outliers. So I transformed the problem into an ordinal classification problem. Ordinal classes are classes that retain their relationship to one another. For example, class 5 would be greater than class 2 or class 3. I bin the tweets by percentile. Each bin has 20% of the tweets in them, and there are 5 bins total. To use ordinal data, I have to use special prediction and loss functions. The first model I used was an attention-based long short-term memory model. The attention mechanism provides interpretability and improved performance, and an attention value is computed for each word that indicates how important that word is. LSTMs are especially good at predicting sequence data and natural language processing. Here's a diagram of my model. The input is embedded and sent through a bidirectional LSTM, where the attention value is calculated for each word. This is recombined in a weighted sum with the encoded layer from the LSTM. This is then concatenated with the LDA data, the metadata, in grams, and fed through a feed-forward neural network. I'll explain what LDA, metadata, and engrams are later. This is sent through binary classifiers where we get our output. The CNN model is good at picking out words and phrases. Here's the diagram. It's the same as the LSTM, but the convolution, instead of an LSTM, I use a convolution. I use 3, 4, and 5 convolutional window sizes. The first thing I did was I used latent reach size allocation. What this does is it takes a tweet and assigns it a topic vector, indicating how much it thinks that tweet belongs to a list of topics, where the topics might be things like war, politics, or they're topics generated by the actual algorithm. So they might be something not interpretable to humans, not interpretable by humans. Next, I used engrams. These are just sequences of 3 or 4 words in a series, or 1 or 2, any amount in words in a series. I make a big vector of whether or not a tweet contains a certain engram, and then I feed that through the feed forward with everything else. Next, I use global word vectors. I use these to give my CNN and LSTM something to work with. This encodes each word in the tweet as a vector, and then each tweet itself is a matrix of word vector values, which I then feed through the models. And I use metadata, so I looked at whether a tweet contained an image, a hashtag. To get output from a model, I had to use a series of binary classifiers, and I counted how many of those binary classifiers exceeded a threshold. For example, I computed everything through I did the LSTM and CNN, etc. And then at the end, I concatenate that with the other data, the LDA, the metadata, and then I feed that through a fully connected layer, which is connected to 4 binary classifiers, specifically sigmoid binary classifiers. And then I count how many of those exceed a certain threshold. To backpropagate on this, I need a loss function. So I encode I encode my training set y as a ordinal encoding vector, which is this, and then I use this equation right here to calculate loss and backpropagate on. So essentially, I just calculate the loss on each of the binary classifiers separately. And then I sum them together and then backpropagate using that. To evaluate, I used normed macro mean absolute error. What this does is it normalizes the deviations between the classes and then sums them together. So it's a score from 1 to 0, where 0 is the perfect score. The CNN performed best with a 0.291, and the logistic regression performed the worst with a 0.329. Random guessing scored a 0.398, so all of the models performed better than random guessing. The CNN performed best. I'm surprised that the LSTM did poorly, because the LSTM itself is designed for sequence data like tweets are, and natural language processing, which is what tweets are. All of the models perform better than random guessing, which is good. And the keyword and n-gram recognition seem most important in models, hence why the CNN performed the best. In the future, I want to look at how the top tweet algorithm impacts the why certain models do better. I think that the top tweet algorithm looks at n-grams and keywords, and hence why a model that's good at picking up on those would perform the best. And I want to find out why the LSTM performed poorly. I think it's because it overfit, but I'm not sure. I'd like to thank Dr. Ramakant Kavaluru of the University of Kentucky, the Math, Science, and Technology program, the Kentucky Young Researchers program, my friends and family.